All right, take it away.
Okay, so welcome everybody. Today I will present you with PMM Hackathon. I will show you a few examples and walk you through them, both for percent memory and CXL mem programming. I will briefly introduce what a percent memory is, although I expect that you probably already know about this. I will also discuss a few basic things about CXL memory, how those two mix together, and how you can port your applications from percent memory to CXL memory if you desire to do so. Okay, so let's start. First, if you would like to know more than what I present today, then you are free to go and look at the book that we have written some time ago. It is free to download, so feel free to just scan the QR code or go to the link which is showed here on the right on the bottom. And this book will have many interesting topics that you might be interested in. It will also cover most of the things that are discussed in the examples that I will show today. So it's a really good deep dive if you're interested in that. Okay, and before I go to the actual hackathon stuff, I will. So I want to show you the logistics, how you will access the website, how you can play with those examples, discuss some basic information about percent memory and CXL, and then you will have some time to play with the examples and possibly also ask questions. I can hang out a bit, so if you have any questions or concerns, then we can also talk about those. So the hackathon will be hosted on a pmmhack1.pmmhackathon.io. You can go to that website right away. There will be a login page. I will show you how to access that in a moment, but this is where all the examples will be hosted. And it can support multiple users, so no matter how many people we have, hopefully we can host all of them. There are a few recommended examples. The first three ones are specific to percent memory, and they discuss very basic things like mapping percent memory and what you need to do to make sure the data is actually persistent. And there are also, those examples also cover some more high-level use cases like key value stores and so on. So you are free to check them out. I will walk through probably the first one with you, just to show you how the entire infrastructure and examples work. After that, you are free to choose any example that you are interested in. There are very different ones, and they range from C, C++ examples to Python and Java ones. So hopefully everyone can find something interesting. And I will also go through all of those things regarding the website in a bit. So first, I will say a few words about what a percent memory is. As I said, just the basic information. And this is the slide that you've probably seen a few times already. This is just showing where percent memory fits in the storage memory hierarchy, right? So this is a technology that can be used and is used usually as a middle layer middle layer between DRAM and slower NAND SSDs or flash drives. And percent memory is generally the term percent memory is generally used to describe technologies which allow programs to access memory, non-volatile memory, and it's a directly byte addressable memory. And the content of this memory is non-volatile and is preserved across power cycles. It has aspects that are like memory and some aspects that are like storage, but it doesn't typically replace either memory or storage. Like I said, it's usually used in conjunction with them. And as you see on the slide here, the latency and the performance usually fits right in the middle between those two tiers. And it's quite similar to CXL. I will also show how this relates to CXL in a moment, but this is right now mostly percent memory specific. And on this slide, you can see what are the different ways that you can access percent memory. So the easiest way is to use the APIs that you can see on the left. So we can just use this as a regular SSD. You can use traditional standard file APIs. And in that case, percent memory is basically just a fast SSD. If you want to leverage percent memory in a more optimal way, you can use it through a PMEM-aware file system. So here on the right, you can see this light blue box where we have PMEM-aware file system. It can be ext4 mounted with a special flag or any other file system that supports percent memory. And in this case, what we have is a way to access contents of percent memory without going through much of the overhead introduced by the operating system. So normally, when you want to persist contents of a certain file, you use system calls like msync to make sure that the data is written to the media. Otherwise, the data might just reside in the page cache and will not be persistent until operating system decides to do so. For PMEM with PMEM-aware file systems, we don't have page cache because it's basically not necessary. As I said, percent memory is byte addressable, so we don't need the page cache. And with those PMEM-aware file systems, we also have an optimized way for flashing, which allows you to skip the msync operation and hence operating system calls entirely. And this will be explained in more details later, but the most important thing is that if you want to use percent memory in the most optimal way, this is usually the way to do this. Okay, and Intel has developed a percent memory development kit. This is an open source collection of libraries, and those libraries provide different level of support. So there are libraries for low-level programming. There are libraries that expose transaction APIs, stream data structures, and other things as well. Those libraries are fully validated and performance tuned for percent memory. So it's often crucial to use them instead of coming up with your own implementation because there is a lot to cover regarding, for example, different architectures and different even generations of CPUs. So there might be non-significant performance differences between different generations, and those differences are covered, and there is a logic to provide the best performance based on that in the PMDK libraries. One thing to note, however, is that due to the Optane discontinuation that was announced some time ago, some of those libraries are no longer actively maintained. So you can still use them, but you should be aware that there might not be support for some of those. And you can read more about this on the pmem.io website. Here is the link. You can click, and on the blog, you will see an announcement, and you can basically just learn which of the libraries are still supported and which are only in maintenance mode or are basically not maintained anymore. This slide presents you with a list of those libraries. It's not a full list. It just shows you what different types of use cases PMDK covers. So on the bottom here, you can see a low-level support for percent memory. We have libraries like libpmem or libpm2. This is basically a library that implements an easy-to-use way of mapping percent memory for an application and implements those optimized flashing instructions. We also have support for remote percent memory. So this mostly covers use cases where we want to have access to percent memory on a different node through RDMA. On higher level, we have libraries that provide transactional support. So we have interface to create a percent memory resident log file through libpmlog. We have libpmopt that allows you to transactionally allocate objects and provides you with a way to modify those objects in a consistent manner. So we can think of it like something similar to a database, but with object granularity. We also have a libpm block, which is an interface to create array of PM resident blocks of the same size and atomically update them. There are also, to some of those libraries, there are bindings to different languages like C++, C, Java, Python, and so on. Today, however, I will mostly focus on this green box here. So this is the volatile use for percent memory. And this is because it's also something that is quite important in the era of CXL memory. And as you will see, use cases that were present for volatile, 4% memory in volatile mode will be very similar to use cases with CXL memory. And some of the tooling, some of the applications don't even require any changes to support CXL memory in this context. Okay, so with that, let's go and discuss CXL memory a little bit. So I won't go into much detail about CXL specific features here, but I just want to give you a short overview of it. If you'd like to know more, there are great materials and presentations on SNIA website and on, probably even today, there might be some talks about CXL that you can listen to. But in short, CXL is an interconnect standard built on top of PCIe. It facilitates cache-coherent memory access between CPUs and supporting PCI-attached devices. Those can be pure memory devices, like Type 3 devices, or accelerators. And CXL distinguishes between those by introducing CXL cache, and CXL mem protocols. CXL also supports memory pooling and sharing. So this is useful if you want to, for example, attach the same device to multiple hosts and dynamically provision that memory. Memory is connected through CXL can be exposed similarly as percent memory, as I said previously. I will show what that means exactly in a moment. And a few slides back, I showed you the where percent memory fits into the storage memory hierarchy, right? And CXL basically fits into the same gap. However, CXL mem protocol expands this heterogeneous memory hierarchy even more, because with CXL memory, you can have basically any possible medium hidden behind it, right? So the specific access latency and performance characteristic will actually depend on the medium and on the controller that is used for that CXL memory device. Right, the most common use cases that I can think of for CXL memory is to have this CXL memory built with DRAM, with high bandwidth memory, or even with PMEM, with percent memory, with non-volatile memory. And there are also some products that combine some of those or have, for example, SSD or flash storage with some DRAM cache built into the CXL memory, which behaves still even slightly differently than just a pure memory system. But still, it uses the same protocol, and we still can use the same tools and applications to deal with that. Just keep in mind that the performance characteristics will be different and will depend on the actual medium. CXL devices can provide both volatile and persistent capacity, and this can be true even for a single device, right? So on a single device, you can have both volatile and persistent memory in some ratio. And this means also that it should be pretty straightforward for most use cases to transition from PMEM to CXL. On this slide, I won't go through all of this, but if you are aware with some of the percent memory provisioning tools, this slide might look slightly familiar to you. There are tools that can be used both for PMEM and for CXL to manage, for example, DRAM and PMEM regions. This is, for example, NDCTL that you can see here. And the way that CXL can be exposed is pretty much the same as with persistent memory. So we can expose this as a headless NUMA node. I will also discuss what a NUMA node is in a second. We can expose this as a character device, so through a DevDAX. And we can also create basically a file system on top of persistent memory or CXL device and have all the benefits that come with file system, like, for example, permissions and so on, right? One difference is what tool is used here on the bottom to actually create memory regions from CXL or from PMEM. With persistent memory, specifically with Intel Optane, you could use tools like IPMCTL to provision and create those memory regions. With CXL, there will be other tools like CXL in Linux that will allow you to do basically the same thing. But most of the tools on the upper layer stays the same. Okay. And on this slide just highlights what I mentioned before, that transitioning from PM to CXL is pretty straightforward. So today I will focus mostly on two cases from here. So the first one is exposing CXL or PMEM as a system RAM, or as a separate NUMA node. And basically, what this allows you to do is to extend the capacity of your system with extra memory that can be used for any purpose whatsoever. You don't need any changes to the application. You can just run non-modified applications on top of this, and it will work fine. You will just have more capacity. If you want some more control, there are libraries and there are tools that you can use to specifically allocate memory on a specific memory NUMA node. And I will also show you this as part of the examples. And the second case is basically a volatile use of FSDAX. So this is a case where we create file system on top of the before mentioned memory. And we can utilize all of the file system APIs, or we can map the file into memory and directly access the underlying content. So for PMEM, what you could do is to just mount the PMEM-aware file system, like ext4 with DAX flag, and just use files mounted on that file system. For NUMA, or for CXL, an alternative approach could be to just create a TMPFS on top of an existing NUMA node. And basically, with that, you achieve very similar thing, and you don't need any extra tools to do that, right? You just use existing functionality of most of the Linux distributions. And briefly, these slides will just describe what NUMA node is. As I mentioned, this will be the main focus for today. So you might know this, but in Linux basically divides the system's hardware resources into multiple software abstractions that are called nodes. And Linux then maps those nodes onto the physical cells of the hardware platform, abstracting away some of the details for some architectures, right? So those software nodes may contain things like CPUs, memory, and I/O buses, right? Here on this example, I basically showed that we might have a two-socket machine with, some amount of CPUs on each socket, and with local DRAM for each socket, and PMEM or CXL memory attached to each socket. So in this case, we would probably have 4 different NUMA nodes. One NUMA node would represent this local DRAM memory along with the CPU cores that are local to this socket. And the second NUMA node would represent PMem and CXL. That would be a headless NUMA node. So that means it wouldn't have any associated CPUs. And the same would be true for socket 1. So in total, we would have 4 different NUMA nodes. And on Linux, there are different tools that I will also demonstrate, which you can use to learn how this topology looks like and what are the hardware or what are the performance characteristics. So basically, you can decide which NUMA node to use for your application, which to use for allocations, for example. Okay, so that was the initial background. And now I will go and try to show you how you can use the PMem hackathon examples to learn more about the things that I just mentioned. So let me just open the workshop page. So as I said, this is the link that you can use to access. You can go there right now, pmhack1.pmhackathon.io, and to access the examples, click Request Access button right here. And then, by the way, just to make sure, can you see my screen with the web browser?
Yes, we're good.
Okay, great. So once you click the Request Access button, you need to provide your name and workshop ID. Workshop ID is here on the slides. So this is a CMSI Intel, all lower letters. When you create request access, you will get username and password, which you can save and use for logging into the hackathon in future. So let's just click login. And as I said, there are a few recommended examples. I will go through them with you with basically the first one. Let's start with this one. Okay, so let's see, just this one. Okay, and maybe first, before I will jump into the example, I will also show you what else you can do on this website. So here on the main page is the list of examples that you can just browse through. If you click on this menu, you also have a way to download the slides. So if you just click here, you have access to the slides that I present, and you can go back to them if needed. There is also a way to access terminal for the machine. So you will be redirected to your local Docker container, which you can use for any experiments. All the examples are run in this Docker environment, but if there is something else you would like to experiment with, then feel free to use this terminal interface, right? And you can also see what resources are available on that server through this terminal. Okay, but let's start with the first example. So this one focuses mostly on persistent memory, and it demonstrates that PMem can be exposed to the application as a file. So this is one of the modes that I mentioned previously. This example also contains some extra information about flashing and consistency guarantees. So feel free to go through it later in more detail. I will just jump through to the actual code part. First, you see that on the system we have basically a few terabytes of persistent memory, and that this memory is exposed as a PMem0 device. This device is mounted to /PMem mount point, and we use PMem-aware file system. In this case, it is ext4 with DAX flag. So DAX means that it is persistent memory aware and that you have direct access to the content of the file. There is no page cache, and you can use the optimized flash that I mentioned before, skipping the operating system calls to make the data persistent. And you can run the same command in the terminal that I showed you, and you can see that perhaps it will return a different result based on the current usage of the persistent memory. Okay, so let's go to the actual code. In this simple example, this is an example written in C that just shows you how to actually use this memory mapped files. So in this case, we will use mmap system call to just map the file system, to just map the file, and then use standard memory operations such as strcpy or memcopy to write the data. Then we will use msync. So this is the simplest case. This is not the optimized flash that I said previously. The optimized flash is covered in the next example. So here, if you just go to the editor here, this is the entire code that is needed. You can modify the code as needed, and you can see, you can play with that as needed. But the most important part is here. So first we need to map the file in question. Those are the flags that are usually needed for mapping percent memory. You can learn more about those also in the links that are provided. And so once the memory is mapped, we just get a normal pointer to the memory, which we can use to write to it using standard memory operations. Here you can see this memory call where we just write hello percent memory to this memory. And then we call msync. So this is a standard Linux system call that flashes all the changes to percent memory, and it would work as well for normal file systems with normal storage devices. Instead of this msync, there is this optimized flash operations that I mentioned, and it is covered in example, let me see, it is covered in example F. So if you are interested in that, take a look at this and you will learn that you can do this more efficiently with percent memory and with PMDK. When you go through this code, you can click here to build this. The binary will be generated, and then later there is a simple script that runs this binary and shows that the string that we wanted is actually written to percent memory. So we just create an empty file, we show initial content, which is 0 in that case, we run the binary, and we hex dump the file. So it should print what we just written to the memory, which is hello percent memory. It's correct. Okay, so this is the first very simple example. The next ones from example A to example F are all connected to percent memory, and they go into various details of different libraries. So for example, example B shows you what are the benefits of persistent memory optimized key value store. This is a libpmkv library. Example C shows you the transactional API that I mentioned before, mostly using C++ bindings. Example D is, again, a pretty simple C program that solves a basic problem on percent memory and utilizes the persistency features. E is another C++ example, and F is, as I said, a low-level example that shows you how to use PMDK to leverage flashing in most optimal way. If you just use higher level APIs like PMKV or transactional APIs, you don't really need to worry about that because those libraries handle the flashing and any consistency changes automatically. Okay, so I will skip over those, but feel free to go and deep dive into them if you want. Right now, I will show you example G. So this is an example which shows you how you can use percent memory in a volatile mode. Still, we will use the file system support here and memkind library. Memkind is also a library that was developed not only for PMEM, but for general heterogeneous memory usages. So there is a link here to a memkind man page where you can read all of the APIs and learn more about the library itself. But the example is pretty straightforward, so I can just describe what is going on here. The first thing we need to do is, similarly as in the first example, we need to map the file system into memory. In memkind, we have a helper function which is called memkind create pmem, where we just pass path to the file we are interested in. This file should be located on file system that is mounted on persistent memory, and it gives us a certain kind, pmem kind in that case. Kind is basically a memkind word for memory source or memory location that we will use for future allocations. So once this is done, once we created the kind, we see here that we can use memkind allocation functions. So memkind exposes functions that are similar to malloc or free, but that allow you to select where the memory is actually allocated from. So you have more control over this. In this example, we have some simple logic that decides where to put a certain allocation based on the allocation size. So if the allocation is big, then we will allocate the memory on persistent memory. If the allocation is small, then we will just allocate it in DRAM, which is a pretty common heuristic. So here we just utilize memkind malloc function and pass that pmemkind that we just created before. And you can also use memkind to allocate memory from DRAM, just like you would use malloc or new. This is by just passing memkind default parameter. Just like before, you can edit the code if you want, you can build this, and then there's a very simple program that will just run the binary. And as you see here, we have an output that shows some of the allocations were done from pmem, some of the allocations were done from DRAM. And this program will also work with CXL-based memory. So as I said, we can provision CXL memory and persistent memory in a pretty similar way. So if we have file system that is mounted on CXL-backed memory, then you could use the exact same program to access that memory. Okay, so this was pretty simple. And next, I will also show you how you can learn more about topology of the system that you have and how you can choose where to allocate memory if that memory is exposed in a different way. So examples M and N focus mostly on cases where we have memory exposed as NUMA nodes. So this is the case that I explained to you recently. And here you can find some links to better description of what the NUMA node is, if you're interested in that. And there is also a links to some of the documentation that explain how to configure CXL or persistent memory in this mode. This is something that I won't cover too much right now. The hackathon system is already provisioned in a proper way. So we have persistent memory exposed as a separate NUMA node, but if you are interested in how to do it yourself, then you can find the links right here. So first, I want to show you the hwlock command. And this command is a Linux utility. It allows you to learn more about the topology of the system and also about some of the performance metrics. So with hwlock, you can, for example, list all available NUMA nodes, learn about distances between those NUMA nodes, which represent relative latency, and also some other memory characteristics. So here you can see an example output. You can see that we have 3 NUMA nodes on this system. So this NUMA node, P0, corresponds to a socket 0 with local DRAM. You can see we have 251 gigabytes of DRAM. NUMA node P1, it is a second socket with the same amount of local DRAM. And we also have a third NUMA node that consists of persistent memory. It is a headless NUMA node, so that means there are no CPU cores associated with that, but it has a bigger capacity, like you would expect from persistent memory. The next comment that I showed allows you to see what is the latency between those different NUMA nodes. So HWlog prints this matrix that you can use to learn how costly it is to access memory from one node to another, or copy memory from one node to another. As you can see here, it's also quite clear which one represents the PMEM NUMA node. In this case, it's NUMA node number 2. And you can see this by noticing that this NUMA node has the largest relative distance, which makes sense because persistent memory is generally slower, has higher latency than DRAM. And you can also learn about some other attributes of the NUMA nodes here. So you can learn about things like capacity. This just prints you the total available capacity on the NUMA node. You can learn about bandwidth that you can expect from this particular NUMA nodes. And again, here it's pretty clear which one is persistent memory because it has lower possible bandwidth. You can also have things like latency with distinction for read and write latency and some other metrics as well that you can learn about by just looking at the hwlook ls command. So this is from a basically administrative point. But if you would like to actually leverage those NUMA nodes in an application in a different way than just extending the total capacity and relying on the operating system to handle that, you can do that also using existing Linux capabilities. So in this example, it's a pretty simple C program that just relies on a libnuma library, and it shows you how you can allocate memory from PMEM or from CXL that is configured as a separate NUMA node. So in this case, we just use mmap. We don't provide any file path here. So this will be an anonymous mapping, as you see here. And once we mmap the memory, we can use a Linux syscall mbind to specify which NUMA node we are interested in. And with this NUMA node, with this syscall, what we pass here is the mask of the NUMA node that we want to allocate from. Here we have a helper function that helps you to select this. In this example, we just select NUMA node with the highest capacity. So we just iterate over all of the possible NUMA nodes using the NUMA-CTL or libnuma APIs and select the proper NUMA node. Then we pass that information to the mbind. And after this is done, we force the actual page allocation. So this is the place when we write something to the memory, this is where the actual allocation happens. And later we can, using another helper function, verify that the memory was actually allocated on the node that we wanted. And we also have here a call to a normal regular malloc function. And similarly as before, we force page allocation. And this will be important when we run the example code and we see what happens if we use some of the Linux capabilities to influence the allocation for the entire process. So let's build this program. We have binary here, and now we have simple script that runs the binary 2 times. For the first time, we just run the binary normally. And for the second time, we use NUMA-CTL capability to bind the process to a certain NUMA node. So as we know, NUMA node 2 is connected to persistent memory. So this will mean that all allocations, no matter if we used mbind or not, will be fulfilled by allocating from persistent memory, basically. So let's run this. And this is the first output. So as you can see here, when we explicitly called mbind, we actually allocated from NUMA node number 2, so from PMEM. when we used just normal malloc, we allocated from NUMA node 0, which is local DRAM or local NUMA node to where this process is actually running. So this is a memory that is closest to the running process, basically. If we run the binary with membind equals 2 flag, what we see is that it doesn't have any effect on the first stage on allocating using mbind, but it does affect how malloc behaves. So in this case, even though we haven't changed the code in any way, we see that malloc returned memory that is on %memory. So this is a very convenient way of making sure that all the allocations in a particular application will use a specific NUMA node. Okay, so that would conclude this example. You can feel free to deep dive into the code and also to the helpers. There is one other example that might be interesting here. So all of the things that I discussed are pretty low level. And in some cases, you don't really need to focus too much on which particular NUMA node you want to use. In some cases, what you are interested in is just allocating memory with a certain characteristics. So for example, if you are building an application, let's say it's some kind of caching solution. So you might want to have an indexing data structure, and you want to have a way to store the actual data somewhere. So for that kind of application, it would make sense to allocate the index data structure on fastest possible memory, or the memory that is closest to your application, while having the actual data stored on a memory that has the biggest possible capacity, like PMEM, right? Because there will be a lot of data probably. So again, using memkind, you can achieve that in a pretty easy way. You don't need to implement all of the code that I just presented before. You don't need to know the exact topology of your system. You can just utilize high-level hints for the memkind. So in this case, you can see that memkind exposes a few predefined kinds, which, as I said, can be thought of as memory sources, with names like this. So there are kinds for lowest latency memory, kinds for highest capacity, and also a few others that I didn't list here, but you can learn about from the memkind man page. So in this case, if we want to allocate memory that has the lowest possible latency from the perspective of the process that we're running on, then we can use a call like this. If we want to use the NUMA node or memory that has the highest possible capacity, we can use this memkind. And this program, as you see, is much simpler than the previous one. It doesn't deal with syscalls directly. It abstracts it away. And furthermore, memkind also implements a heap manager. So there is embedded pooling, memory pooling inside memkind. So that means you don't need to allocate memory in a big chunks like with mmap. With mmap, the granularity is usually 4 kilobytes. With memkind, you can allocate much smaller objects, and internally, memkind will just request memory from the operating system when it is needed. And this improves performance quite a bit if you need to do smaller allocations. So here, the example, the main function is pretty similar to the previous example, with the difference that we are just using these high-level functions here. So here we just allocate memory on the highest capacity, force the parity allocations just as before, and see where that memory ended being allocated from. So if we build the program and later run the program, we can see that if we request the allocation to be fulfilled from the highest capacity node, it will come from node number 2, which again makes sense. This is PMEM. If we request the allocation to be from a lowest memory that should be lowest possible latency, we will have allocation from node number 1. And this is probably because this particular example was run on NUMA node number 1, on the socket 1. So the local DRAM is the DRAM that has the lowest latency. And if you are interested in learning more about those kinds of things, and in Memkind in particular, there are also some blog posts that explain more advanced use cases. So in some cases, you might want to not only allocate memory on a particular tier, but also have some way of migrating the data, for example, or have some way of making sure that you use specific ratio of DRAM to PMEM. So one example, if you have both DRAM and CXL or PMEM in the system, then you might want to use both, to a maximum extent, and make sure that each application have pretty similar performance characteristics. So Memkind also exposes certain features that allow you to make sure that whenever you allocate memory, it will keep a constant ratio between DRAM and PMEM. So the same percentage of allocations will go to PMEM or CXL versus DRAM for different allocations. There's a blog post that you can see here and you can learn more about. Okay. So let's go back to the examples, and those would be the examples that I would recommend going through in more detail if you are interested in that. And I think that would be all from my side right now by going through those examples. If you have any more questions to me, then I'll be happy to answer them. The slides, as I said, are available here through the menu. You can always go back to them. And in each example and on the slides, there are additional links to the materials that you might find useful, and especially the configuration step and administrative steps that were not covered in this presentation. So yeah, that would be all, I think. Thank you.